Hi, and welcome to Quality Engineering. We're going to be going over the Introduction to Quality Engineering, which is from your Chapter 1 reading. I'm just going to cover a couple of highlights and add some additional commentary from my perspective to hopefully supplement what you've read or are going to read in the text. And you'll need to finish Chapter 1 reading before you do the quiz that is posted on PolyLearn. So first of all, let's talk about what is the definition of quality. And you can see there are two definitions listed on the screen there. Fitness for use and quality is inversely proportional to variability. The second one there, quality is inversely proportional to variability, is the one that we're going to be thinking about as we go through the quarter and is really the modern definition of quality. And you can see the graphs listed here below. This is trying to visually show you that quality is inversely proportional to variability and then the associated costs. So this is for transmissions, as you can see in the title of the figure, but let's think of something different. Let's think about it as how many miles tires will last. Sorry, let me okay. Let's think about how long tires will last on your car. So if we say tires are going to last 10,000 miles, so anything that lasts longer than that is awesome. Anything that lasts less than that is not so good. And the fewer miles it lasts, the worse it is. So you can see when we have less variability, which is the taller curve here, that we have fewer going below the 10,000 miles mark. And there are fewer going above, but there's still some going above too. And so the more variability, you're going to get maybe more people who, or a few more people who are happier, but you're going to get more people who are unhappy about their tires not lasting as long, right? So some dissatisfaction. And you can see the cost associated with that is people are going to have to get their tires replaced more frequently in this little area that I'm highlighting here. And actually, in this case too, they may just end up not using your company anymore because the tires don't last, enough of them don't last up to what the target mean is here. So you can see that the costs are more expensive with that increased variability too in the example I gave. And the text talks more about the example of transmission. Think about maybe your GPA too, right? Do you like getting a range of grades? And I'm sure none of you go as low as D's or even C's probably, up to A's, or you're kind of happier when you're around an average, kind of tightly around an average of B, for example. So we'll talk about that a little bit more when we get to control charts, but we'll want to be thinking of what is our target or what is our mean, which is what we have, what we have here, and then what is the variability around that. But keep in mind this definition here, quality is inversely proportional to variability. So the less variability we have, the higher quality we have. And we could maybe debate that a little bit in class as well, if you disagree with that or what you think about it. Next, we have how much quality, I guess is maybe one way of saying that we want to have. So you're all very familiar with this top curve here, which shows our 3 sigma from the mean, 3 sigma below and 3 sigma above. And we all know from statistics courses that plus or minus 3 sigma from the mean covers 99.73% of the population. And so what that translates to is 2,700 defects per million parts, which is probably pretty good. And you can see there's the percent of the population covered. But when we talk about 6 sigma, which is something you'll read about in the chapters, we'll talk about a little bit later, is that's a higher level of quality. And that is saying not only do we have, are we going 3 sigma standard deviation, 3 standard deviations from the mean, but we're allowing for a 1.5 shift in the mean plus 3 standard deviations from that shift in the mean. That gets us out to 6 sigma, as you can see here. And when we go out to 6 sigma, which is a term, I think Motorola is the one we give credit to starting this off, that's only 3.4 defects per million parts. So that's much better than the 2,700. So that's what we mean when we talk about 6 sigma quality 3.4. Now this is another conversation we can have in class. How many companies do you think achieve that? Do you think that's realistic? Is it appropriate for all products? So think about that a little bit and we'll talk about it in class. And I was right, it is Motorola 6 sigma concept right there for us. Okay? So that's what we mean by 6 sigma, and we want to design to get as few as defects as possible. Then we have, in addition to designing for Six Sigma, I want to talk about how that relates to productivity improvement. So you can read all the information here. I'm going to talk about it just briefly. We've already talked about quality. Definition of quality is inversely proportional to variability. That's the modern definition. Well, so what is quality improvement is reducing the variability in processes and products. So it can be a product like a car or a tire or a transmission, all related to the car, or it can be a process, reducing the amount of time it takes to process a purchase order, for example, something like that. Reducing the amount of time you spend in a grocery line checking out, those kinds of things. And so we have three different what I would call quality improvement processes. We have DFSS, which stands for Design for Six Sigma. So I just explained Six Sigma in the prior slide, where we're trying to get a very, very tiny amount of defects per million parts, 3.4 if I remember correctly, defects per million of parts. And so this lists all the things that requires you have to have allocations of resources in order to do that. Do you have the capability, like is your design, is your process in place so that that is even possible to do? And it relies for very predictable product quality because you know you're going to have so few defects. Then another one is lean, which that term should all be familiar to you guys from your IME 223 process improvement fundamentals, as well as other classes too, where lean is all about reducing waste, eliminating waste, making the process better through less time, through less materials, through less resources. And these are some of the tools that we talked about in process improvement fundamentals, and I'm sure you've seen them in other classes as well. But by eliminating waste, eliminating cycle time, you're reducing variability and improving quality as well as you go through. Hopefully. The last one listed here is DMAIC. DMAIC. That stands for Define, Measure, Analyze, Improve, and Control. Those terms are all described in your text, so you can read more about that there. And so that process should remind you of something that we talked about in IME 223, right? The infamous threaded, select, record, examine, etc. So you identify a problem, get data about it, collect data, examine that data, make recommendations for improvements based on that, implement it, see how it goes, and then start over again. And so that's basically what a DMAIC process is as well. And so all of these are, each of these three are different quality improvement processes. Whichever one you want to use is fine with me, in my opinion, is best. And then also from the reading, don't forget our infamous Plan, Do, Check, Act cycle, which is the Schuhart cycle that Deming made popular. So very, very similar. Again, quality improvement process. You can see the words there. We're figuring out what we're going to do, make the change based on data. Did we get the results that we wanted? If we did, yay, keep it in place, standardize it. If not, then make some changes and go through. So continuous process. So I'd throw that one as another quality improvement process. Okay, next let's talk about some terminology. So you've already read about the 8 dimensions of quality from the text and completed the assignment associated with that, so that you're going to be prepared to bring to class the analysis, taking a product against those. And let's kind of use that as a framework for going over some of the terminology. So we have quality characteristics. We have physical, sensory, and time-oriented here. So for example, length. Something we might think about in length is how many miles a tire will go before it fails. And I would say that that's related to the performance dimension of quality, because it's how well is it going to perform. Another one that we can talk about is weight. Oh gosh, you guys probably don't even remember the old bubble TVs, but how heavy they were. So if you had to take it in for repair, you'd have to practically get a dolly to wheel it out of your house, versus now these flat screen TVs are so flat and lightweight that you could just pick it up with one hand, put it in your car, and take it in to be serviced. So more easy serviceability from that perspective, for example. Then we go down to sensory. So look at these 3 here. The sensory ones, I would argue, have a individualized component to them, because what I think is a good high quality color, you may not. And so maybe standard black as a phone cover is fine for me, but we know that the iPhone, the smartphones all have multicolors, patterns, etc. And I would say that that is related to, we can relate offering the different colors is related to the features dimension of quality here. Then we have appearance too. And so the way I choose my cars is when I'm driving down the freeway, whatever car I think looks the cutest, if I pull up to that several times, well then that's the car I'm going to go check out to see if it, has other quality dimensions here, performance, reliability, etc. Price as another one too that meets my standards, but appearance is a big one for that. And so that is an aesthetic dimension of quality. And I would argue that for each of these, my opinion could be different than yours, so it could be individualized. And then the time orientation ones listed here, you can see these are all dimensions of quality that we have listed up here. So I've already talked about serviceability a little bit with related to the weight of the TV. Reliability would be, let me just look at my notes to be sure, that your car starts every time, right? It's very reliable. Your car starts every time. Durability, an example might be that your car starts every time, whether you're in nice weather, Southern California, Central California where we are, whether you're in the 120-degree heat in Arizona in the summer, or whether you're in the minus 50 degree weather in Alaska during the winter. Okay, so those are some different characteristics of quality. And then we have, within those characteristics, we have either a variable characteristic or an attribute. So a variable means that it's a non-integer, as listed there by the continuous measurement. So back to the tire, it could go 5,000.3 miles, 200.7 miles, etc., but it doesn't have to be an integer, so it's a continuous measurement. Versus an attribute is it has to be an integer. So for example, color, if we're going to be looking at how many cars are pink versus how many cars are white. No, even I would not buy a pink car, but it's on or off for the attribute characteristics. So the part is either good or bad. Would be another one. It passes or fails. So the attribute, it has to be an integer. It's going to be a count for the characteristic, quality characteristic that we're looking at. And that is also relevant when we start talking about control charts, is the type of control chart that uses a variable characteristic is going to be slightly, not in looks, but in calculations different than the attribute characteristic because the underlying statistical properties are different. And we'll talk about that when we get to control charts. Additionally, so what is a control chart, since I mentioned the word? It is data shown over time so that we can see the performance of the product, for example. So we have a center line would be our mean. So let's say in the tire example, on average tire goes 10,000 miles. The upper control limit means that maybe it goes 11,000 miles, and the lower control limit means maybe it goes 9,000 miles. So any point that falls outside of these control limits then would signal us that we need to do something, that the process isn't performing as we would expect. We'll talk about this a lot more when we get into control charts. This is statistical based. It's all based on actual data from the performance of the product that we're looking at. But we have the nominal value. I don't like using the word target because this is database, so it's whatever the mean is, and then the upper and lower control limit are typically 3 standard deviations away. So 99 would capture 99.7% of the population between the upper and lower control limits typically. We'll talk about that a lot more later. But that is the control chart and some of the terminology associated with that. And then we also, and that would be a continuous variable. Well, actually, no, we have control charts for continuous and integer variables, so for both variable and attribute. Then we have defective or non-conforming products. So I've already started talking about tires, and look, I have a picture of a tire here. So this defective or non-conforming mean it is fatal defect is the way I like to put it. It's a no-go. You're not going to be driving around on this tire here. That it has to be trashed. It has to be scrapped. It is no good anymore. It's defective. Fatal defect, cannot be used anymore. Versus a defect or nonconformity, because not all defects make the product unusable. So for example, this cake here, it has a lot of cracks in it, so that's a defect. It's not, as beautiful as we would like it to be, but I'm willing to bet that most of you, and certainly I, would still go ahead and eat this cake or a piece of cake, even though it has some cracks in it. So not all products containing a defect, aka this crack here, are necessarily defective, meaning a fatal error that you have to throw them out. Then also the chapter talks about just statistical methods. So you know that you have to take IME 326, you have to take your stats class as prerequisites coming into the quality engineering class, because quality tools, several of them are based on statistical methods and statistical principles. So we have design of experiments, and this again is taken from your text, where it's more time consuming and it's not necessarily applicable to all products or processes. Then process control, which is where we're going to spend a lot of time this quarter, is not quite as time consuming and can be applied to more processes than design of experiments. And then finally acceptance sampling. So design of experiments, you can see the terminology there. What I really want to emphasize is it's an offline technique. We're not going to be doing a design of experiments to see which material we want to use to improve the life of the tire in the production line, because what if we pick a material that is going to make the performance worse? That would cost us a lot of money if we made a lot of tires with that, right? So it's an offline technique. We're going to do some experiments with different mixes of rubber, whatever we use to make tires, to find what is going to be the longest life with the most effective cost, etc. And that's going to be offline experiment that we do. And you learn about that in IME 326. Then statistical process control, which is what we're going to spend some time on here, is there are many different types of control charts and other problem-solving tools that we're going to be going through in the quarter. And these are online techniques. So we're gathering data on the line. Sometimes it's destructive to the part. Sometimes it's not. We just take a few pieces out, make a measurement, put it back in line, and then go on. And then we see what's happening as the product is moving through the line so that we can make adjustments if needed, or understand the variability is within the controls of what we'd expect, back to the control chart we just saw on the prior slide, and we just keep the line moving. So statistical process control. And normal distributions, Poisson, are some of the underlying processes. That's not the word I'm looking for. You know what I'm looking for. Statistical distributions, that's the word, that will be underlying for the quality characteristic that we're going to be looking at. And then lastly, acceptance sampling. That's based on incoming inspection. So we'd be taking 3 pieces out of 1,000, and if those 3 pieces are okay, then we say all 1,000 are okay and pass. If one of those 3 pieces are bad, then we say the whole lot has to be inspected before we can move it forward, or maybe just reject it back. So there's some statistical analysis and coming up what those sampling plans are, but the sampling plans have all been developed for us, and so we'll take a look at that and apply that later as well. All right, so those are 3 methods that use statistics that support quality engineering. And then I'm going to give you some time to look at this slide on your own and bring it into class, and we'll discuss this question here. So within this process of inputs we can control, so the type of raw material, the quantity of raw material, for example, the uncontrollable inputs, and you can think of some of what that might be that you don't have complete control of, result in the output of what the quality characteristics after you complete the process on the raw material, and then we do the measurement and then go through the cycle here. So what I'd like you to do is, in this process that's shown here, where is acceptance sampling appropriate, where is statistical process control appropriate, and where is design of experiments appropriate to improve quality, and why. So we'll talk about that in class, and you can read more about that in the text as well. And that is it. So these are the learning objectives that you have for this introduction to quality. So between the reading, this video, your class prep activities, and what we're going to do in class, you should be able to meet all of these. Okay, I look forward to seeing you in class. Thanks.